All right, thank you very much, Sahil and Rupal. It's my honor to be here today. What a fantastic presentation so far. It got me excited with all of the different events and things that you guys are doing to get students and alumni and actually partners in the industry excited about what we're going to be doing looking towards the future. So I thought I'd spend a little bit of time today just giving you a little bit of background about myself, what kind of I've experienced in a space career to date, and really what I'm excited about moving forward in space in general, okay? So I'll do a quick introduction. I'll give you a little bit of my background. I won't bore you, but I really want to do it to kind of give you an idea of you don't have to specialize in space in school or growing up to actually make a big impact in space moving forward. I'll share a couple of the differences that space applications and designs bring versus other platforms. I want to give you maybe 3 quick examples of some of the exciting space efforts that Northrop is currently involved in. One of those will be kind of looking back towards the Earth. One of those will be looking away from the Earth. And then one of those will be kind of in the middle with our constellations and where some of our satellites are. And then we'll spend a few minutes talking about trends, kind of looking forward and what that means to you, our future in our space business moving forward. And then if you're interested, let's chat a little bit about careers and how you can prepare for them and what kind of opportunities there are, okay? All right, so quick introduction. So I got my bachelor's and master's in electrical engineering at Georgia Tech. I was really interested in electromagnetics, RF design, and I did a minor in optics and power distribution as well. So you notice there's nothing in there that's very space specific. I'd always liked space, but I didn't think that that would be a career choice for me. I started my career out at Harris Corporation. I started doing some RF design, some power divider circuits and things like that. Wasn't really sure what they were going to be used for. I was waiting for my clearance to come through. Once I got my clearance, I understood then that they were for a restricted space program. And that's what opened my eyes to space. And it was really exciting. And even though I can't tell you what I worked on way back then, it still excites me because the mission that we produced is still working. It's still going on today. It's well exceeded its life. And it makes me proud that I was a part of something that is helping each and every one of us. I did some phased array testing to help with that application. We're going to talk about the importance of that coming up soon as well. I joined Northrop in 2004, started out doing a lot of airborne programs. So you see some of the jets that I worked on, managing programs pretty much on the radar kind of front end of those. But then I also got involved in more restricted space programs, very much involved on the payload side, designing, building sensors that go onto different satellites to do different things. Then I was lucky to also be part of a program management role on the ground-based systems piece of space. And that really opened my eyes. Sometimes we just think of whatever's up there in space is really it, right? That's the thing that's doing all of the work. But we tend to forget that there's a whole infrastructure on the ground that enables those missions, that gives them, exceedingly new capabilities moving forward. So until I saw that piece of it, I didn't really understand the whole aspect of a space mission. So as you can see, my background, hardware, software systems, some program management, some homeroom and functional organization management, doesn't say space in there, doesn't say aerospace, right? But I think you don't have to prepare yourself specifically for it. I love the examples that Rupal went through. Those kind of creative thinking and thoughts like that will really allow you to have a great career in space if you so choose to. I put a smattering of pictures on there just to note that space is very generational, right? Generations before me, they can tell you to the day where they were when we, put a man on the moon. For me, it was a space shuttle. Growing up in grade school and high school, I used to watch all the launches. That just excited me that we could go into space and bring that shuttle back and then reuse it to go back there again, right? The space ISS, it just was cool to me that we have a base now in space that we can do things, we can bring people back and forth. That's just something I never thought I would ever see. So that's exciting to me. The Hubble telescope, the pictures that this telescope brings back are just breathtaking and awe-inspiring, right? SpaceX with their reusable rockets. I mean, I was on YouTube watching those coming back, and you can see everybody in SpaceX excited about that, and I was as well. So the more we do with kind of our reusable technologies, that's going to drop that cost down to enable us to do more things moving forward. And then finally, for me, the James Webb Space Telescope, a lot of people I know are excited about that. And we're going to talk about that in a little bit. But I think every single one of us has 1 or 2 things in their generation that they can point to and go, wow, that was really cool, right? So I can't wait to see what the next generations bring us moving forward. Okay, so what's different about space? So let's just start with the obvious thing, the environment, right? It's very different. So I remember when I was working on airborne programs with those different fighter jets I talked about, yeah, you know, tens of thousands of kilometers means different things for that environment. But think about hundreds of thousands of kilometers when you go up into space with all of the different orbits that you have there. So certainly pressure, vacuum, the extremes in temperature, solar radiation, as well as other radiations and other nasty things up there that you have to prepare for to make sure your vehicle or your system works, right? And that gets to the illities. There's a really big part of space design and application that revolves around these illities. One of them happens to be reliability. Reliability is really just the prediction of your performance once you're operational. So you want to make sure that you've done everything possible so that your system works. And that's why, as I talked about earlier, I'm really proud that we built and delivered a system that exceeded its lifetime. That's fantastic to get, you know, even more utility out of something. So durability and maintainability play large roles underneath reliability. Durability is just what it sounds like, right? How durable is your product that you put up there? So there's a lot of different things that goes into durability. Some of those things I'm going to talk about in a second are redundancy. If one piece goes down, can you kick in another piece that can kind of take over? Part selection is a big deal to make sure those parts can withstand those environments that I just talked about. And then maintainability. It's really easy for me to put a radar onto a fighter jet, and if it doesn't work, well, okay, it might be a problem if it was a mission, but it can come back down and can be serviced and be right back up there. An illity that I can put on here is availability. All of this goes to availability. And that's a spec or requirement that our government customers levy on us. We want this thing to work 99% of the time, you know, 80% of the time. And as you see, we're going to talk about trends moving forward. We are seeing missions that certainly are Class A, meaning they have to work 99.9999%, right? To maybe Class C, where it's a demonstration. We want to try something out. If it doesn't work, that's okay. We've advanced science, we've advanced technology. So those illities play a big role in what you're delivering for space applications moving forward. So what are some key focus areas on space designs? Number one, requirements flow down. We really need to understand what the mission is and make sure we translate that mission down to every single piece part, maybe even a resistor on a board level, to make sure that every piece is doing its part to accomplish what we need on that mission. I can say that's true for any application, but certainly for space missions, it's that much more important because you really only get one chance to do this, right? Part selection and pedigree. We have to really pay attention to the parts we pick. Again, back to those solar radiations and all those nasty things in space, that we got to ensure that these parts function. Now we look at things like parts, you know, maybe they fail because of something, but they can start back up again. Maybe a reboot is okay. Others, a reboot may not be available. Once a part fails, it fails, and you don't want to lose a multi-million or perhaps multi-billion-dollar system because a part fails. So making sure you understand where those parts came from, the testing that goes involved with those parts, that's a big part of space design. Redundancy, I mentioned, we have to look at the overall reliability. Perhaps we need to add 2 or 3x some of the systems to make sure that if one goes down, that's the way to go. Now, certainly the restrictions of cost may be a problem. We can't just keep adding things on there. Maybe weight now becomes a problem. So you really have to be creative in figuring out how you can get the best reliability within the constraints that you're given. And then finally, comprehensive testing. The test plans in our space designs are pretty thorough. There's a lot of different, not only tests, environmental, electrical, physical, but you have to do them more than once. Sometimes you have to do thermal cycles 5, 6, 10 times to make sure that the cycles that this space system is going to see as it orbits around can still function. So a comprehensive test plan is a major, major part of how we get our space designs verified, validated, and then delivered. And then over to the right, I just wanted to make sure everybody understood the different components of space systems. And this is very simple, right? Starting with a mission, that's something you'd probably expect, right? Do I need a constellation? Do I need a family of satellites? Is it one? Is it geosynchronous? Is it going to be stationary? So that's kind of the mission level. What are you trying to get? What's the mission of this design or this space application? The second piece is, okay, now that you got the mission defined, spacecraft, right? Something's got to go up there and do something, right? So now we, typically talk about buses. Does this bus need to move in and out of orbits? Does it need to move up and down? So different propulsion techniques that require our buses to position themselves in the right place. Star trackers help with that. Just remember the old sailors with their sextants. That's the same thing, right? That's a core piece of technology that allows the bus or the spacecraft to position itself where it needs to be. And then reaction wheels and other pieces of technology kind of allow the spacecraft to position itself properly so it's not spinning out of control, right? Then we get to payloads. And payloads are pretty much just different sensors that are bolted onto the spacecraft, right? What are you trying to do? Are you trying to take pictures? Are you trying to look at RF energy? Are you trying to listen for signals? Those are all the different sensors. So they can be optical, RF, comms. Are you just simply trying to communicate? Television and radio satellites, right? Taking information from one side of the Earth, beaming it down to the other side. So that's where the payloads come in. They're the sensors that do the kind of the hard work, I'll say. And then finally, as I mentioned before, operations, a key role in maintaining a mission of a space system. Command and control activities, tasking, telling a satellite when they need to turn on, when they need to pivot, when they need to do something. And then once they do something, getting that data down to the ground and having people analyze that data. It sounds simple, but there's a huge technology and core of data analysis that goes into space. Machine learning, AI, all of those things that we maybe associate with computers and other industries, that's a big piece of space as well. So don't forget that the operations piece really enables the mission to succeed, as well as it allows new capabilities to help with that. And we're going to talk about that in a second as well. Okay? All right, I want to hit you with 3 quick kind of space uppers that certainly I'm proud of, and I hope you are too. Everybody knows about the James Webb Telescope. There's a picture, a mock-up of it there on the top, and on the bottom, there's a picture in one of our clean rooms out in Space Park in Redondo Beach, where the James Webb Telescope is being designed and built, as you see, and tested as well. So 5 kind of key things I want to leave you with. Number 1, this effort is pushing frontiers, right? We're going to get a view that we've never gotten before. It's going to allow us to go back in time 13 billion years to see what really happens when some of those stars either exploded or died, or how did things form right in the universe. It's a huge step forward. Literally, we're going 1 million miles away from Earth, and I'm really looking forward to next year. That's when it's planned to launch. It is a revolutionary tool. It is going to be the largest telescope in space. The sun shield, which is kind of those aluminum sheets that you see on the bottom there, each one of those is the size of a tennis court. So imagine deploying something that large in space once it gets up there. It's collaborative. That's really exciting. NASA, the Canadian, European space agencies, there's a lot of different companies and agencies that are involved to putting this together. And I want to highlight University of Arizona was one of the pieces here. And you're going to hear me talk about universities and what they bring to space now and in the future. And that's where you play a role. And then finally, it's a game changer, right? What we learn from this telescope will probably help us rewrite some of the science textbooks that certainly I read, and maybe what you're reading right now. And my hope is it inspires that next generation, right? I talked about a generational thing. So I'm hoping students, people, kids will start looking at this going, I want to do that. I want to do something as cool as that. So for me, certainly it's a game changer moving forward. Number 2, I want to talk about SPIDER. This is the Space Solar Power Incremental Demonstration Research Program. This is really cool, and I use that term loosely here. What the Air Force Research Labs is doing, we're partnered with them, is to try to figure out a way to take solar energy in space, convert it to RF radiation, and beam that down to the Earth where it's needed. So this is kind of really interesting to me because it takes 2 of my loves, space and kind of RF energy, right, put together. And that picture on the bottom there, that's a mock-up in a lab, and what you're seeing is just light above. You see the solar cells collecting that light. That card there transfers that energy into a little phased array, and that phased array directs that beam down to that little card that the person is holding, and you see a little LED light. So it's basically demonstrating that, yes, we can take light, convert it into RF, capture it, and then use that RF energy to turn on that LED. And I have a movie, and you can go onto YouTube and look at it. The person kind of moves that card up and down, and as she moves the card down, you'll see the light getting dimmer, which shows that it truly is energy that's turning that light on. Then you'll see somebody's hand come in the middle, which will block the light and kill that light. So that started out about a year ago with Caltech to demonstrate this. Now our company is taking the next step, which is to try to prototype, make that tile much smaller. And by the way, that's 60 by 60 meters in that picture that we want to get to. That's an acre. So imagine the folding and the mechanics that's required to get that deployed in space. But if we can do this, we can get a lot of energy beamed down. We can use our phased array technologies to move that beam of directed energy to wherever we need to go. So you can imagine why the DoD is interested in that. They may have an area of interest. They may set up their camp there, put one receive tower up, and we can give them all the energy that's required to maintain their mission using this technology. So very exciting stuff. And again, collaborating with Caltech, so universities play an absolute major role in some of our discoveries moving forward. And then finally, the third space effort that I want to talk about. This is really exciting to me. And this just happened back in February of this year. Our mission extension vehicle. This is the first time a commercial venture has allowed a space satellite to attach itself to another space satellite that's already been out there to increase its life. And there's a lot of pictures there. I don't want to go through all of these. There is a YouTube video you can click on to see what's going on here. But basically, our vehicle has a jet pack kind of propulsion, electrical propulsion system. When it's launched, it gets up there in space. It will seek the target. And in this case, it was an Intelsat satellite that was out of orbit and didn't have life anymore because it was out of orbit. It will find it. It will navigate itself towards it. It will hook it. It will, grab onto it, pull itself there, and then mechanically attach itself to the satellite. There are no electrical, communication, telemetry attachments. It's purely mechanical. Now it's going to serve as the new propulsion and attitude control for this satellite. So we were able to successfully grab onto it, and we took it to the orbit where now we've extended that satellite service for 5 more years. So you can imagine how exciting this is for our commercial entities, folks that can expand their markets, protect their assets as well, and just enable much more performance moving forward. And I talked about those ilities before, and I didn't mention it, right? I was going to say, well, you can't go up there and fix things once you launch them. Well, now we can. So that's really exciting to see what we can get out of this technology moving forward. So I'm excited about these things. And you know what's really cool about this? All of the 3 things I just mentioned, you can go on YouTube, you can go on the internet, they're all unclassified. A lot of the different space technologies before, they weren't. I couldn't tell my family or my friends what I worked on because a lot of the things have been restricted. They certainly still are, but it's exciting to see some of these new commercial ventures moving forward as well. Okay, let's talk about trends in the space industry. So certainly traditional space development, when I started, and certainly well before me, you had to be a very large company with a lot of deep pockets, and you had to have a large infrastructure put in place in order to explore or even enable space mission capabilities. So NASA, the defense contractors, folks like that were really only solutions you could go to when you wanted to do something. A lot of cost plus contracts. And what does that mean? When you have a contract with the government, cost plus means I'm going to do my best within this confinement of dollars, but because these things are risky and there's a lot of development, I may not really, hit it on the first try. We all know the different engineering principles. I may need additional dollars. So we share that risk. The government as well as the industry leaders share that risk. You're going to see me talk about in the future, we're moving away from these cost plus contracts and we're going to fixed price, which is kind of shocking when it comes to these hard development projects. So what's allowed us to transition these trends? Involving technologies and enablers. And I just put a few of the things there. Certainly computing, right? I know when I was in school, even in grade school, the computers I was using, you laugh at them now, right? The cell phone in my pocket right now probably can do more than that entire, computer room that I worked in when I was in high school or in grade school. So computing power, giving us the ability to process and do all of these things in a fast manner certainly has enabled some of our solutions moving forward. Propulsion systems are very different. If you look at the rocket engines from before and today, certainly we can lift much larger weights. That allows us to have more complex buses and sensors that I talked about earlier. Materials technology, that's enabled us to do a lot of different things. Look at the spacesuits that the astronauts earlier used versus what we're using now. It gives them that freedom and flexibility. And Rupal talked about the difficulties of those gloves and those helmets and things. And so a lot of advancements in those material technologies is allowing us to do more things in space that even if we could have gotten up there, we couldn't have done before. And then certainly communications and navigation. Now we can talk to anybody without any delays. Navigation systems allows us to do things a lot more autonomously. The Galileo and things like that Sahil, you talked about. Increases in technologies there are enabling kind of set and forget type solutions where we launch them and then we wait for many years and awesome things come after that, right? So what are the trends that I see? More accessibility. So what does that mean? I don't have to rely on these large defense contractors or organizations and hundreds of millions of dollars to do things. If you look at the picture to the left there, this was taken in October of 1946. This was the first picture taken in space. If you look at the picture to the right, that happened in 2017. That's a balloon and an iPhone. And you can see the difference in performance and quality that you get. And it probably took tens of hundreds of millions of dollars in $46, by the way. And you look at the one in January and it was maybe a few hundred or $1,000 total, right? So that's what I mean by accessibility. We're reaching into our universities. Hobbyists now are doing things in their backyard that people couldn't do 20, 30, 50 years ago, right? We looked at the telescope. Now I can get one of those telescopes, put it on my deck, and get pictures and views that you probably couldn't get 50 years ago, or I would have had to spend a lot of money, right? Cheaper and smaller. This helps us in a lot of different ways. Um, Cost, certainly, but we can also put a lot more systems up there to do different things. Autonomous, that's a trend that we're seeing. A lot of the decision making, I talked about the mission piece on the ground. We're putting smarts up in the satellites so the satellites can decide for themselves what they think the next step needs to be without waiting for somebody to tell them what to do from the ground, right? And then integrated. Imagine, just like we talk about robots and rovers on the ground talking to each other, swarming if they need to. That's what we're looking for satellites to do as well. Let them talk to other satellites within the constellation and optimize themselves for the best performance moving forward. So really exciting stuff, taking parallels from key technology enablers that we don't associate with space, but it's gonna really get us to different places than we're used to. And again, for me, that's exciting, and I think that's really exciting for our nation and our world itself. Okay, so finally, are you interested? Does any of this stuff resonate with you? If you are, careers in space, there's a ton of them, right? Number one, they're very mission oriented. If you love the mission, if you love what you want to do, making an impact not only on yourself, your family, but the nation, this is a place for you. If you like defining technologies, you will be working with technologies that people don't even know existed. And if you go on the restricted side and get your clearance, they won't even know for 20 years what you've been working on. Again, kind of stinks you can't talk to your family about it, but you are at the forefront of technology. Simple reasons why we get into science and engineering, discovery and exploration. Space continues to provoke us, and this is a great field for you to just explore and really try to push those boundaries. And if you just like solving problems, this is a place for you. It's difficult. It's difficult to get things up there to do what we wanted to do, but people creatively find solutions. And just kind of look at where we are now. I look at just 10 years ago where I was, and it's exciting and amazing what we can do. We need all kinds of backgrounds in space, right? System, software, hardware. You didn't see me say aerospace or specifically astronomy or space specific, right? If you're creative, if you're innovative, if you like to collaborate, that's what we're looking for. So if you have any of those kind of key things or you're passionate about that, that's what we want. And honestly, anybody can get a job in space. A lot of you can get a career in space, but most of you who are on this call already have an interest or are passionate. You can follow your passions having a career in space. In our company, we love to say, we'd like to define the possible, right? So just me, while I put these charts together, it's like, look, it's impossible to direct energy from space, right? It's impossible to extend a life of a satellite once it's died in space, right? It's impossible to make a time machine, right? It's not, right? We're making these things now, and I can't wait for you and the next generation to help us, take us and do even more impossible things moving forward. So I put those pictures back up there. These are the things that resonated with previous generations and myself. It's your turn, guys. What are you going to put? I can't wait to see what you guys bring to the table and advance our nation. And if you're interested in a job, I'm certainly looking for some help. There's some contact info down there, and maybe we can talk in the chat room later. I will tell you, I'm proud to have an engineering organization across the country. I have 21 alumni from University of Michigan right now. Help me make it more. And those pesky Buckeyes, I have 6 of those. So let's keep beating them with more University of Michigan alums, all right? Thank you very much, and looking forward to any questions that I can help you with.